didn't hear you come in. You're early. Well, might as well get started. Hello, my name is Michael. As you can tell by my ill-fitting lab coat, I am a scientist, a professional scientist.
Pierce the heavens with your science!
And I'm here today to tell you all about the physics involved in bot shots. What are bot shots? Well, Billy, these are bot shots. They're little auto-transforming transformers with a built-in battle game. You crash them together, look at little symbols on their chest, and that's how you see who won. And they're cheap, they're fun, they're durable, and totally awesome. At least if you're a geek like me. However, what you don't need to be a geek like me to understand is that there's actually a lot of physics going on when you crash these little guys together. And we're going to break those physics down bit by bit. Why? Why not, I say? And you know who else dared to say why not? Bobby Kennedy. Not to brag, but as far as smarts go, I'm pretty much on a par with him. Anyway, let's break down all the ins and outs of our toys using science!
Science!
To begin, we'll need to know the mass of the bot shots. There are 4 here that we'll be looking at: Optimus Prime, Bumblebee, Starscream, and Barricade. Now, I do have one more, Sentinel Prime. However, while the other 4 have very well done spring mechanisms that deploy pretty much whenever you want them, Sentinel Prime does not. So, we're just going to leave him out of this whole ordeal. I've massed each bot shot individually, and this was the result that I got. Multiplying this by the force of gravity, 9.8 meters per second squared, we can see that the weights of the bot shots are as follows. That's just vertical forces. What we're interested in are the horizontal forces that go on when the figures collide with each other. So let's all be mature adults and crash our toy cars together so they can turn into toy robots. By filming the collisions of the bot shots, we can measure their average velocity pretty easily. And we'll need to do all the combinations, just to make sure we got all our bases covered. Like, say, if Optimus Prime and Bumblebee got in a fight, and they just decided to be all like...
Science!
By looking at this footage more closely, we can determine their acceleration during the collision, and from that, figure out the amount of force each bot shot feels during the collision. First, let's look at the collision at normal speed. Now, let's see the collision at normal speed again, because that was awesome. Next, we'll slow things down so we can find out the velocity right before they collide. Then, going frame by frame in a program called Tracker, we can see how long the collision takes, i.e. how long it takes for the bot shot's velocity to reach 0, deploying its mechanism. Now, since we're dealing with such minuscule time frames, we need to actually just take the velocities from before and after the collision, find the difference between them, and divide them by the total time frame. In this collision with Bumblebee and Barricade, we can see that the numbers are negative 9.816 repeating for Barricade and 5.972 repeating for Bumblebee. Now, that seems rather high, but remember how that collision looked. That's fairly violent for objects of such small size. Also, when we use Newton's trusty second law, we can see that the actual forces here are negative 0.
Correction. Upon consulting with a colleague of mine in a very professional manner... Hey, Tim. Hey, Tim. Hey, Tim. What are you wearing? No, seriously, I got a question for you. I realized that I was slightly off in the calculation of the velocities and... not velocities, accelerations and forces. Meaning that the acceleration is in fact negative 39.43 repeating meters per second squared for Barricade and 38.8 repeating meters per second squared for Bumblebee, meaning the forces are negative 0.706 newtons for Barricade and 0.684 repeating newtons for Bumblebee.
Which is fairly reasonable. Now, when we apply that to all the different collision combinations, except Optimus and Bumblebee, because Bumblebee's a wuss and can't make Optimus transform, we get these numbers. But that's not all. There's also momentum, a function of mass and velocity that's conserved during collisions. In layman's terms, speedy thing crashes together, speedy thing bounces off each other. Now to figure out momentum, we'll need this equation. Now, since we already know the velocities before and after the collision, this is just a matter of plugging things into things and seeing what comes out. Never mind. Let's just put the results up when we do all the fancy mathematics. There you go. And that just about covers it, with the exception of spring tension. But in order to do that, I'd have to take these guys apart, and I don't really want to have to do that with any of the ones I got, so I have to buy extras. So I'm just going to let you guys have the spring tension equation and try it out for yourselves, because that's so professional of me. But what about that Sentinel Prime fellow? What do we do about him? I'll tell you what we do about him. And with that, I'll say it's been quite a ride teaching you about the science behind just one small segment of my plastic crack habit. I hope it entertained to some degree, and maybe even informed to some degree. And I will see you all in the bright future, where maybe someday you can become a professional scientist just like me.